for coming to the second lecture of this morning. So I'm Yifan. I'll be lecturing on the topic of generalized symmetries and their gauging, also known as generalized gauging in a specific family of quantum field theories, but it's already quite rich in this context, namely the D equal to 2 conformal field theories. And here is and you should also make comparison to the nice lecture given by Shuhen and also this morning and also for the rest of the week, in the sense that I'll be talking about the continuum version of various interesting concepts that he described in the discrete lattice model. And here is a rough outline of the set of lectures I will be giving. I will start with the basics of two-dimensional CFTs. That will probably be the focus of the first lecture. For those of you who have studied CFTs before, this will be a quick review. And those of you who are relatively new to this subject, this will hopefully provide you with the working knowledge to have fun with using these 2D CFTs to discover and understanding features of topological defects and the corresponding generalized symmetries. And after that, we'll move on to discuss symmetries in the traditional sense, coming from groups, and the related notion of discrete gauging, which is conventionally known as observables. And then later on, we'll generalize these notions. But before doing so, we'll introduce this generalized mechanism, or generalized kind of concept to describe symmetries in terms of topological defects, which I'm sure you have heard of from other lectures last week. And then the mathematical framework, which is very concrete in the two-dimensional context, that underpins the mathematical structure of the topological defects, namely fusion category. We'll say many things about that. And then lastly, we'll connect this topic 2 and 3 in this generalized context to describe the gauging that one can implement for the generalized symmetries as generalization to observables, and to the relation to think about the generalized gauging as another kind of topological objects in the two-dimensional quantum field theories as topological interfaces. And for the first lecture, there are plenty of references on CFT that you can find online. But here I highlight the few. So one is one of the canonical references on CFT that you can find is the big yellow book by DiFrancesco et al. But for some quick reading, I'll refer you to Ginsberg's lecture note. You can find the archive at DH 9108028. This archive number probably is not necessary because Ginsberg is one of the inventors of archive. And also a nice lecture note if you want to know about CFT also in higher dimensions. Many of this concept I described in the first lecture is also applicable to higher dimensions. I will refer to David Steffen's Tarsi lecture note, 2016 Tarsi lecture notes. And also this very nice set of lecture notes by Slava at EPFL school. That discuss much details of CFT in higher dimensions. And I'll also refer you to a more recent lecture note from Xi Ying in 2017. Again, Tarsi lecture notes, which provides a concise overview of this modern approach to two-dimensional CFT based on the bootstrap philosophy. All right, so let's start with the main part of this lecture, namely a basic introduction or review of CFT. Before going to more technical details, let us briefly motivate why conformal field theories, which is CFT for short, are interesting objects to study. So first of all, we should define what CFTs are. Okay. So CFTs, I believe all of you have studied QFT, and CFTs are just special class of quantum field theories with an additional symmetry known as conformal symmetry. And this symmetry has a lot of consequences, which we'll spell out in the rest of the lecture. And at the mathematical level, this is a symmetry described by the group SOD, 2. So for the moment, I'll focus on the general dimension. Later on, we'll specialize to the dimension where D is equal to 2. So the CFTs are always quantum field theory with the conformal symmetry. It's a group that includes the point inquiry group as ISO d-1, 1, working in the Lorentzian signature. And it has, in addition to the generators you're familiar with in the point query group, namely Lorentz transformations, mu, and translation p mu, has in addition a dilatation operator. We generalize the scaling transformation. And in addition, somewhat more mysteriously, the special conformal transformation, which you can thought of as a conjugation of a translation by the so-called inversion transformation. And this inversion transformation, which is denoted by I, sends a point in the space-time to its inversion, as defined as follows. Okay, its inversion defined with respect to the unit circle in this convention. And in this lecture, question, yes?
For the whether CFT in general is a theory without Lagrangian.
That's right. The CFT, the definition of the modern perspective, although many examples of CFT come from either a lattice model in the continuum limit near critical point, or quantum field theory, RG fixed point or quantum field theories. But the abstractly, CFT can be defined in terms of algebras of local operators, which is described in a bit, which no longer require the definition of a Lagrangian, definition in terms of Lagrangian. Okay. And in this lecture, so I'll be focused on QFT, not arbitrary QFT, but QFT with several nice properties, namely they're local. Okay, this notion also came up in Shu Heng's talk, and also we'll be focused on CFTs, which are or QFTs. They are unitary. Okay, that makes sense as a unitary quantum mechanical system in the Lorentzian signature. And furthermore, we'll assume our QFT is and the corresponding CFT is compact. Namely, when you study the theory on a compact spatial slice, then there's a discrete spectrum, okay, with respect to the energy. And the fact that you have the conformal symmetry, as it follows from Noether's theorem, there's a distinguished operator in the quantum field theory, namely the stress tensor T mu, that has a property that is symmetric and they satisfy the conservation, namely T mu nu is 0. And the CFT arises from the special cases where this distinguished operator satisfies additional operator equation, namely is also traceless. Okay. And these two conditions ensures that you can construct the family of currents, which are Noether currents for this big symmetry, okay, that you can construct it by contracting one of the indices on these stress tensors, this rank 2 symmetric tensors, with the vector field, denoted by epsilon. Okay, and these epsilons satisfy the so-called, so they are known as the conformal Killing vectors, because they satisfy this set of equations. Okay, this is a defining conformal Killing vector equation that generalizes the usual Killing vector equation. With this equation, you can check together with these operator equations that this current is always conserved, and they define the Noether currents for this SOD, 2 symmetry. And the usual Killing vectors that associated with the symmetry of the point query group correspond to the special case where the conformal Killing vectors are Killing vectors, namely the right-hand side is identically 0. Now that you have a symmetry, as this is the case with any symmetry, which is the case including the case of space-time symmetry as well as the case of internal symmetry, which has been the focus of this school, you can organize operators and states in your theory in terms of representations of the symmetry. So in this particular context, the operators, local operators in the theory that you can imagine in the case of a lattice model built out of your lattice degrees freedom, and in the case of a Lagrangian quantum field theory built out of your elementary fields, these operators, they need to form conformal families, which is another way to say that they furnish representations of this conformal group SOD, 2. And these conformal families are individually characterized by the lowest weight states, and they are known as the conformal primaries. And they are labeled by quantum numbers, which are eigenvalues with respect to the Cartan-Sabel algebra of the symmetry SOD, 2. And they are labeled by explicitly by the dimension, the so-called dimension, scaling dimensional operator, which corresponds to eigenvalue under the dilatation operator. And then the spin J, which denotes the eigenvalue under the various generators of a Lorentz group. Okay. And J in general is a vector because you have multiple spin generators in higher dimensions. And correspondingly, well, in addition to operators being organized into representations of the conformal group, correlation functions of this quantum field theory with this special symmetry are also highly constrained. And the constraints take the form of conformal word identities. Okay. And together, they lead to a drastic simplification on the dynamics of the quantum field theory with the symmetry, yet still rather rich that it captures many interesting physical phenomena. So to give you some evidence for why there are interesting quantum field theories with this gigantic symmetry, let's address physical context. What kind of physical context this enhanced symmetry and the corresponding quantum field theory arise? So one important place where it arises is at the second order phase transitions of various quantum and statistical models, where there's a continuous descriptions, and the continuous description are given by such quantum field theories. And these are quite universal, that even happens as ubiquitous as in the case of boiling water. And in the quantum field theory context, this conformal field theory also arises as fixed points of renormalization group flows. Again, although there are counterexamples, but generically, at the fixed points, you automatically gain additional dilatation symmetries. And with a number of small caveats, this dilatation symmetry is typically enhanced further to include this special conformal transformation, and altogether generates a conformal symmetry group. And then lastly, I just want to mention that the conformal field theory is also very interesting in the sense that it provides a model for studying quantum gravity via the ADS-CFT correspondence. Okay. And this is one of the main reasons why conformal field theory has received a lot of attention in the literature. Okay, so why? So now that I have mentioned various contexts where this conformal field theory has arisen in physics, and let me explain the reason behind why there are so interesting quantum field theories to study. One interesting feature of them is that they carry the hallmark of universality in physics. Namely, various different physical systems near second order phase transition may be described by the same underlying continuous description, namely a conformal field theory. And they are characterized by a small set of physical data that includes the so-called critical exponents and what we will describe later on, OP coefficients associated with operators at the CFT. And these conformal field theories also give a very powerful non-perturbative approach to quantum field theories. For reasons we'll describe shortly, because as Xiaogang asked before, there's a description of this theory that's independent of a perturbative description based on Lagrangian. And furthermore, because of the connection to quantum gravity via ADS-CFT, this feature also generalized to the case of quantum gravity in the sense that it gave rise to a non-perturbative approach to quantum gravity that's not based on perturbation theory, which is something that you learn from a string theory class. So in this sense, the conformal field theories, they provide some kind of standard candles to study the space of quantum field theories. And in the sense that these conformal field theories are more generic than the free theories. Okay? In particular, the critical exponents that correspond to scaling dimensions of operator in the theory are no longer integers or half integers, which are the case that you see in the free theories. Okay? And these are much more generic.
question about
Yes.
So you have this inversion symmetry. That inversion symmetry is a discrete part of this.
So the inversion, strictly speaking, inversion is not inside SOD comma 2 because it changes orientation. That's right. So this is not connected to the identity. So
no, this is not connected to anything.
That's right. Yeah, it's not connected. That's right. That's right. So strictly speaking, you have to enlarge this group to include inversion.
I see. And also this, you're using the Euclidean signature, so no Lorentz signature?
No, so right now I'm talking about the Lorentz signature.
I see.
As you can see, it's d minus 1 comma 1, SOD comma 2.
So if it's a Euclidean signature, yes. What is this? What is the multiplication for SOD comma 2?
So in the Euclidean signature, then the corresponding conformal group is SOD d plus 1 comma 1, and then this SOD. D is a space-time dimension. Very good. So I should have emphasized that.
Actual plus 1 is
yeah. So the in my convention, D is always a space-time dimension.
Okay.
Yeah. Okay.
But where does D plus 1 come from? This plus. So 1, the comma 1 is a scaling, right? This.
So 1 comma 1 part in the Euclidean signature, you can think about 1 comma 1 is coming from the dilatation, and SOD is thought of as a symmetry. So you think about the symmetry of the cylinder. SOD is a symmetry on the SD minus 1 sphere. And the 1 comma 1 part generates the dilatation. Yeah. Okay. All right. Thanks for the question. And if you have any questions, please feel to interrupt at any point. All right. So these are the nice things about CFT that are make them very the focus of many theoretical studies. But how do we actually study them? Okay, and this is made possible by this definition or formulation of CFT that does not depend on the perturbative description, namely coming from Lagrangian, related to the so-called operator algebra formulation. Okay, this is the alternative formulation of CFT, which is more abstract and more general, does not rely on perturbative Lagrangian. And this is made possible. This makes it possible to study these theories non-perturbatively. And this formulation defines the CFT in terms of some basic data, namely the spectrum, which is a set of scaling dimension together with the spin quantum numbers, denoted schematically by delta and J, and together with OP coefficients, which keep track of, in the rough sense, interactions between these operators. And they are characterized by correlation functions of 3-point correlation functions by the basic operators in the theory. Okay, again, schematically denoted as this set. And once you have this formulation of the CFT in terms of this basic data, you can argue, based on things that I'll explain, that all the general correlation functions are just determined by this basic data. And then furthermore, there are axiomatic constraints on this basic data, known as bootstrap axioms. And this axiomatic constraint has a very simple origin. It's just coming from the basic principles of the underlying quantum systems, namely locality, unitarity, and more subtly, the notion of compactness. Okay? And this gave rise to this bootstrap axioms, gave rise to an axiomatic approach to attack these quantum systems and to solve, and alternatively constrain or derive universal consequences on CFTs. Okay, and this is made possible many powerful results that solve this strongly coupled quantum systems described by conformal field theories.
So in terms of this operator algebra formulation, you need this structure constant.
These are the structure constants.
So the question is that you need infinite number of structure constants to specify a CFT.
In general, yes. In general, yes. So as we'll explain, in very simple models, like the Ising model that Shuhan already talked about from a different perspective, in that case, a finite number of structure constants is sufficient because they are so-called minimodels. But more generally, in general, you have to specify infinite number of structure constants. But they are also subject to infinite number of bootstrap constraints.
Yeah, that's right. Yeah. But the question, do you know that after this constraint, whether there is a generating subset, which is finite number, which is defined whole conformal field? What this formulation is there?
Yeah, so that is not known. So you're asking a very good question in the sense that there may be a more efficient way, at least for subset of CFTs, there are more efficient way to package this data that only involve the small finite subset of information. That is not known. We don't have that language yet.
So at the moment, it's an infinite number of input parameter, but also infinite number of constraint. Maybe at the end is a
well, the point is that because there are infinite number of constraints, in favorable cases, you only need to, there are a small number of input in order to fix everything else.
Okay.
Yeah, but that's in favorable cases. The most general case, we don't know.
I see. Thank you.
Okay. Hey, sorry, excuse me. Yeah. Super beginner question. So two operators have the same delta and j. That's an operator.
No, they do not have to be. So here I'm being schematic. So indeed, that's a very good question. There could be generalities in the sense that once you specify delta and j, there could still be multiple operators. For example, they could be related by a global symmetry transformation. Okay. Very good.
So why is compactness important in this scenario?
So this is compactness for one reason is that I want to have a normalizable vacuum that's conformally invariant to work with, so that I do not need to consider like exotic cases like Liouville. Of course, they are interesting for other purpose, but just for the context of the lecture, I'll be focused on the case when the compactness condition is satisfied. And also another reason I can justify this assumption is that from the models that arise from a lattice model, okay, for example, a quantum spin chain, this compactness condition is satisfied. Okay. All right. Okay. So these are some general motivations for that study CFT. But for the particular purpose of the school, I just want to make the point that this non-perturbative definition of the quantum field theories and the way to describe and solving them using this schematic approach implies that this conformal field theories are the ideal playground to study further constraints from other symmetries, namely in the spirit of the school, the generalized symmetries. Their properties and dynamical consequences. Okay, which will be a focus of the next lecture and the subsequent lectures. All right, so that's very general. Let's now be even more specific. Let's be more specific and focus on the case of CFT in dimension equal to 2. Okay. Because we are working on the blackboard, this will simplify our life significantly, working in 2 dimensions. Again, this is in the high energy terminology, namely D is the space-time dimension. So in kind of matter language, this will be the case when we are working in 1 + 1D. Okay. Question? Yes.
In the dimension larger than 2, do we know that this local data specifies everything, or I guess you can always stack with a TQFT, but could you do something more interesting? Like, is there something?
Oh yeah. So very good question. So here, very good question. So here, a small caveat I should have clarified is that this set of data specifies the correlation functions of local operators. Okay. Of course, there are extended operators, and they are constrained with this data, but they are not fully specified in general. It so happens that in 2 dimensions, as far as all the example I know, this set of data actually also determine the defect spectrum. But this is not true in higher dimensions.
Why is it not true?
Sorry?
Why?
Sorry?
Why is it not true in higher dimensions?
Because you have more non-trivial TQFTs. It's related to the fact that in 2 dimensions, the TQFTs are rather trivial. If you insist on compactness, and in addition, the thing that I did not specify, that there's a unique vacuum, then there's no non-trivial TQFT to play with.
Access modular TQFTs.
Modular.
Yeah, No, that's what we asked. If modulo TQFTs, that specifies everything.
Well, but it depends on whether you include gauging.
Yeah, and also discrete gauging. Yeah. 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 Or if you include, genuine and non-genuine defects on the same time. It depends on a number of small subtleties. Okay. All right. So let's now work in 2 dimensions to simplify our life. And for this purpose, it's convenient to introduce the following set of coordinates for our space-time. And they also call this coordinates z and z bar. These are complex coordinates. R2, which we obtain by weak rotation. So you can think about this as a Euclidean spacetime. So again, this is for convenience. And we can always recover the Lorentzian data by reversing the weak rotation. Okay? But it will be simpler to work in the Lorentzian Euclidean signature. And the first thing we should analyze is the property, whether the symmetry property is whether there's something special to the symmetry property of a conformal field theory in 2 dimensions. As you'll see, this is going to be the case. And the way we discover that is to study this distinguished operator, namely the stress energy tensor, satisfying the constraint, namely it's conserved and traceless in 2 dimensions. And in this set of coordinates, complex coordinates in 2 dimensions, the components of the stress tensor obeying the traceless condition are the 2 independent components, TZZ and TZZ bar, Z bar, Z bar. And I will write their argument as following. Due to the fact that if you study the consequence of the conservation equation, you will find that this T is purely holomorphic. So I'll denote this for short just by T, and then this by T bar. And on the other hand, T bar is purely anti-holomorphic. It's just as a consequence of the conservation equation. Okay. And again, in the 2-dimensional context, there's J is just characterized by the single number, namely the spin. And this stress energy tensor satisfies the condition that the spin and the dimension are both equal to 2 in 2 dimensions. And this property, namely that the T and T bar are separately holomorphic and anti-holomorphic, leads to a drastically enhanced conformal symmetry in 2 dimensions, leads to this enhanced infinite dimensional conformal symmetry in D equal to 2, namely the Virasoro symmetry. Okay, and this is what's going to help us in further constraining how the data is represented, how the data of CFT is represented in this very small set of numbers compared to the full set of correlation functions and so on. And in this case, you can ask where this infinite conformal symmetry come from. And again, they better be associated with currents as a consequence of the method procedure. And these currents are coming from CKVs, conformal Kinne vectors, which have a bigger class of solutions now. They are parameterized by a vector on your space-time. But now the components are more general. They can be arbitrary function. This holomorphic component can be arbitrary function of Z. And anti-holomorphic components can be arbitrary function of Z bar. Okay, and they generate at finite level the following conformal transformations that send Z to a function holomorphic function of Z, and Z bar to a holomorphic function of Z bar. Okay, and the corresponding currents are again constructed as before. By contracting the stress energy tensor with the corresponding conformal Kinne vectors, and they are denoted just as follows. Okay, and you can check that the conservation property of the current is preserved by just requiring epsilon to be a holomorphic function of Z, as opposed to some more stringent restriction. And then there's a convenient basis you can introduce for such holomorphic functions of z and anti-holomorphic function of z bar, which you can take to be monomials in z and z bar correspondingly. And they lead to the charges for this infinite dimensional symmetry. And these are the Virasoro charges that you can define by the following contour integrals. Okay. As you know, they're coming from codimension 1 integrals of the currents, and the currents are constructed of stress tensor this way, and we're taking this basis for epsilon, and this is how you arrive at the expression. And similarly, you have another set of charges coming from the anti-holomorphic component of the current, and this leads to the following they're given by the following contour integral, which represent this codimension integral defining the charges, which you learned from the last week's lectures in the following way. Okay. And this set of charges leads to this enhancement of the working the Euclidean signature of the global conformal group SO3, 1, which is isomorphic to PSL2, C, to the full-fledged Virasoro symmetries. And you have two copies, Virasoro and Virasoro, generated by L and L bar respectively. And there's one more ingredient to this Virasoro symmetry, namely there's an important central element, which I denote by C and C bar. Okay? And to see the origin of the central element, we have to study the commutation relations between these Virasoro generators. And these commutation relations, because these Virasoro generators are built out of stress tensors, these commutation relations can be pinned down once you know the operator product expansion associated with the stress tensors themselves. And that, how do I, okay, this is how I do it. Okay. Very good. Right. Okay, I'll try to make use of the leftover space over here. So can make use of the leftover space here. So the central element focus on the one copy of Virasoro generated by this holomorphic charges Ln. This central element can be fixed by studying the OPE, the operator product between two stress tensors, holomorphic stress tensors T and T. And just from the fact that they're holomorphic, namely they're annihilated by the anti-holomorphic derivative, you can fix this OPE to be of the following form. Together with the fact that they're dimension 2, have spin 2, you can fix the OPE to be of the following form. Up to regular terms. Okay, so these pieces are crucial in order for the global part of the conformal. So namely, this is the global part of the two-dimensional conformal symmetry. Namely, this part, if you want to, if you study the corresponding charges, the commutator of the charges, namely for n and when n takes the value of plus minus 1 and 0, they generate the subalgebra of the bigger symmetry, which correspond to the global part of the conformal symmetry in 2 dimensions. This part of the OP is crucial to ensure that that global algebra takes the expected form, namely the PSL2C. But there's an extra term that's allowed by just the holomorphicity condition together with this scaling transformation law. And that leads to this additional element, C, which after you go back to the expression and compute the commutators using the OPE leads to this central extension. Okay. So I'm skipping some details in the derivation, but you can find in those references. The upshot is that you'll find this following Virasoro algebra. So I'll just write on the right-hand side. Okay, which is something you will. This is the expression you will need to study unitarity constraints on two-dimensional CFT. Okay, so for that reason, I'll write it down. And similarly, so denoted by Virasoro C. And similarly, you have a similar algebra for the right-hand side generated by the antihomomorphic charges. And these two charges, they commute to one another, which will be consequence of the OPE between T and T bar. And I'll leave that as an exercise. Okay. All right. And once again, the global part of this conformal algebra of this infinite dimensional conformal symmetry is generated by this subset of generators L0 and L plus 1, and L0 bar and L bar plus minus 1. Okay. And in terms of the familiar quantum numbers, that delta and J in general space-time dimensions, they are eigenvalues of L0 plus L0 bar. Okay, so these are the eigenvalues of L0 plus L0 bar. And then L0 minus L0 bar has a value. The eigenvalue of this operator leads to the spin that characterize operators in two dimensions. A very important feature of conformal field theory, not just two-dimensional conformal field theory, is this relation between operator and state. They're known as the operator-state correspondence, or state-operator correspondence. Emphasize again, this is a correspondence that holds for local operators in general conformal field theory, namely general conformal dimensions. Sorry, general space-time dimensions. And it's a very interesting direction to understand this correspondence for extended operators. And I believe some of you in the audience have been thinking about that. So I emphasize, again, for the purpose of this lecture, and especially in two dimensions, I can make an excuse to focus on the case of local operators. And the correspondence is a statement between local operators in the theory and states in the Hilbert space on S1. Okay? So where does the S1 comes in? It comes in to think about the theory in the radial quantization. So imagine that you're on the Euclidean plane. And you want to study quantization where the time is taken to be the radial direction. So you think about the radial quantization. So if you take the radial direction to be time, then the Hamiltonian is generated by the dilatation operator, which is L0 plus L0 bar, okay, in terms of the generators of the Virasoro algebra. And we can pick this to be our origin, and this dotted circle to be the unit S1 that we pick to study, to quantize this theory and study the Hilbert space. Okay? And the state order correspondence is a statement that states on this S1 can be constructed by inserting local operators at origin. Okay? And the corresponding state can be thought of in the path integral language as path integral over this region with a boundary condition specified by this local operator at the origin. And if you wish, and the other way correspond to, so that correspond to, this give you this one direction that construct the state from the local operators at origin. And you can reconstruct such local operators by studying from a state on this S1 and then evolving backwards. Okay, evolving backwards. And as long as, so with a small caveat, you take this state to be energy eigenstate with respect to the radial Hamiltonian. Okay, this will give rise to the local operators at origin. And you can also view this picture maybe more intuitively on the cylinder. Okay? And these two pictures are related by conformal transformation, namely sending. So if you take the coordinates here to be z and z bar, and over here the coordinates to be w, which is sigma plus I tau, and take tau to be the Euclidean time along the cylinder direction, and sigma to be the direction along the circle of the cylinder. These two pictures are related by a conformal transformation that sends z to e to the minus I in w. Okay, and in terms of this picture, this S1 maps to the circle on the cylinder. Okay, and this corresponding state I'll denote by the state that corresponds to this local operator O. I'll denote just by the state using the same labeling. Okay, and in particular, the vacuum state on this circle, equivalent on this circle, corresponds to the case where you insert nothing, namely just identity operator. Okay. Again, this is something that will not longer hold in the case you want to study extended operators. Okay, but I'm happy to discuss that afterwards. All right, so to discuss constraints coming from unitarity, we have to specify what is the Hermitian structure. And once we have done that, we can use the fact that the Hilbert space has a positive definite norm to deduce constraints from unitarity on the operator spectrum, as well as other CFT data. To specify the Hermitian structure, we have to remember that the unitarity property will descend from the original Lorentzian theory after weak rotation. So we should also study the Hermitian structure as inherited from the Lorentzian signature. And the place where the Lorentzian structure is very natural is on the Lorentzian cylinder. So you should think about this cylinder. The Euclidean cylinder, where the Euclidean time is tau, is coming from a rerotation of the Lorentzian cylinder, where this is the real time. And on the so these are the Lorentzian cylinder, where t is I tau. Okay. So on the Lorentzian in the Lorentzian signature, Hermitian operator satisfy this usual operator equation, namely if you take the Hermitian conjugate, you get back to itself, okay, with no action on the spacetime insertions in the Lorentzian spacetime T and sigma on the Lorentzian cylinder in this case. Now remember that general operator inserted at T and sigma can be translated from operator inserted at 0 time and sigma equal to 0 using the generators of the conformal symmetry in the Lorentzian signature. In this case, they are just given by translation according to time and the circular direction. And you can write by conjugation in terms of the Hamiltonian and translation. Hamiltonian that parameterizes the evolution in the time direction, and the translation along the spatial circle direction as follows. Okay, again, this H and P are operators that generate time translation and spatial translation. Okay. Now, remember that after weak rotation, the Euclidean operators are related to the Euclidean operators on the Euclidean cylinder with tau and sigma as coordinates, are related to the Lorentzian operators by this coordinate redefinition as follows. I'm using this convention. It does not make a difference, but let me stick to the convention in my note. And then going to taking the complex conjugate on this object, okay, on the right-hand side, and using this property, okay, and using the fact that both the Hamiltonian and the momentum generators are Hermitian. you find that taking the Hermitian conjugate of the Euclidean operator involves, in addition, a reflection of time. Okay, just coming from taking the Hermitian conjugate of the top expression. So the upshot of this discussion is that Hermitian conjugation in Euclidean space-time involves a time reflection. And in addition, a complex conjugation. If the operator, so here I'm assuming the operator itself is Hermitian. So if you start in the form of Lorentzian signature where the operator itself is complex, additional complex conjugation would be needed. Okay? And I put the quotation mark on time is because this notion of Hermitian conjugation in the Euclidean space-time as inherited from a Lorentzian space-time depends on the choice of your quantization. And correspondingly, the choice of time, which is transfers to the spatial slice, which you use to quantize the theory. But the important thing to remember here is that there's a time reflection that's involved when you want to specify what is Hermitian conjugation in the Euclidean space-time. And this, in particular, if you work on R2 using the relation between operators on the cylinder and operators on the plane, given by the conformal transformation, okay? And we'll say more about the explicit way how operators transform on the conformal transformation. But taking that for granted for now, using that relation, let me just state that if you're on R2, Hermitian conjugation is also known as BPZ conjugation. Namely, if you have an operator, a real operator, in the case, let me give the example of a scalar operator, a real scalar operator. You get this additional factor that's coming from relating the operators on the cylinder and the operator on the plane, and using the fact that on the cylinder time is being reflected under this conjugation. Importantly, is 1 over z bar in the first argument and 1 over z in the second argument. And another way to understand this intuitively is coming from the fact that reflection, because time on the plane in the radial quantization corresponds to the radial direction, and reflecting time is nothing but inversion. And this prefactor can also be understood from the conformal transformation of this operator coming from inversion. OK, so this is taking into account relations between operators on the cylinder and operators on the plane. So just for your reference, let me give you this relation, which you can derive using the Weyl transformation, relating the flat R2 to the Euclidean cylinder. So there's a similar conjugation that you can write down explicitly for the spinning case. I will not do that explicitly here. I'll leave that exercise. In particular, if you study the conjugation on the spin 2 operator, namely the stress energy tensor, the Hermitian conjugation, which will be the key in writing down the unitarity constraint, acts by, again, inversion. There's a factor of 1 over z bar to the 4, and t of 1 over z bar. Okay? And this property, together with the way that the Virasoro generators are related by t by the counter-integral, or equivalently by the Laurent expansion of this holomorphic object, you can deduce that the Hermitian conjugate of the Virasoro generators are given as follows. Namely, the Hermitian conjugate of Ln corresponds to flipping the molding number to -n. And similarly, if you do the same analysis for the anti-homomorphic component stress tensor, you find that Ln bar, if you take the Hermitian conjugate, you get L bar minus n. Okay? And once you have this property, you can then go ahead and study unitarity constraint, as we'll come to shortly.
Any questions?
Yeah, about the... Yeah, so when you look at the stress tensor,
yeah,
I mean, really, people typically, when they factorize the 2D CFT, they only look at holomorphic and anti-holomorphic parts. And then they modify the rules for the Hermitian conjugation to where instead of it being 1 over z bar, it's just 1 over z, right? But without doing that, at least the way you've done it here, I would think that it would that the Hermitian conjugate of Ln would be like L minus n bar.
No, so
if you do the contour integral on both sides here, somehow the.
So that may be a common misconception. So you are free, of course, to study a Euclidean CFT in a different Hermitian conjugation structure. You specify your Hermitian structure differently, but that's not going to be the same CFT that's coming from requotation of unitary CFT in the Lorentzian signature. So throughout my discussion, our CFT is always coming from some unitary theory in Lorentzian signature obtained by requotation. Right. And the Euclidean discussion is just a trick to study observables that you can measure in the Lorentzian signature. And for that context, the Hermitian structure is inherited totally from the Lorentzian theory, and you don't have a choice. And this is the answer you get.
I think I agree, but I mean, look, like for instance, in a lot of the references that you gave, eventually they just look at the factorized description, right? And then Hermitian conjugation no longer exchanges z and z bar, so it's not. No,
that's not the correct logic. The reason that you end up with this Hermitian conjugation structure that only close on the factorized part, as you said, is coming from this line of reasoning. Yeah, you can study other representations of Virasoro times Virasoro, where the Hermitian conjugation flips the two. That's a mathematically valid question. It's just for the physical applications, you are obliged to study the case where the Hermitian structure preserves each individual factors separately.
I think I'm still a bit confused, but I'll ask it.
Okay. Yeah, we can.
If there's a further clarification, let's discuss afterwards. Yes. So before we get into the constraints for unitarity, there's one other important important structure associated with CFT is the notion of operator product expansion. Again, there's a lot of interesting things to be studied in this context if you include not just local operators but also extended operators. But for the purpose of this lectures, we'll focus on the case of operator product expansion of local operators. In this context, again, imagine that you're on the plane, okay, and you have two operators. Let's call that OI and OJ. Okay. And then we can choose our quantization. So we work in the radial quantization, and we can choose our quantization to be on this circle, which we pick as S1. And by the state operator correspondence, the way we prove the state operator correspondence more explicitly, this insertion of the operators under the path integral evolution give rise to a state on this circle, which I denote as psi. Okay, so this is what I'm saying. This psi correspond to this operator, correspond to this set of operators acting on the ground state that correspond to inserting nothing. Okay, and this is the state on this S1 that we picked in our quantization. Okay, and then by the state operator correspondence, we can re-represent this state as suppose this is the origin. Okay, this is the origin. We can re-represent our states. Okay, let me use Z1 and Z2 to avoid the confusion. So these are 2 points within this unit disk. And then this is the origin. We can by the state operator correspondence, we can re-expand this state in terms of operators at the origin. And that leads to this following combination. So summing over state by evolving from operators inserted at origin, but weighted by some coefficient, which I denote as Cij, and this coefficient in general can depend on this z1, z2 variables. Okay. And then you can ask, how rigorous is this sum? Does this sum make sense as a convergent expression? And this is indeed convergent. As a consequence, of the fact that we have a Hilbert space, and this psi corresponds to a normalizable state in the Hilbert space. Namely, if you take the inner product of psi with its Hermitian conjugate, this is finite. Okay? And the reason that this is true is because when you take the Hermitian conjugate of a state, you get vacuum on the other side, and these operators are mapped by BPZ conjugation to operator inserted at the inverted points. Okay? And by inversion, around the respect to the circle, these operators are the operators under inversion correspond to operators inserted elsewhere, okay, that are separated from these insertions. And then as a consequence of that, in this correlation function, which are denoted by the inverted operators, so OI. So there are correlation functions of OJ under inversion, OI1. Okay. Okay. Because these operators, using this rule, they correspond to insertions of the same operator at the position that's separated from these locations. There's no singularity in this Euclidean correlator, and the consequence is that this is finite. And from that, together with the fact that we have a Hilbert space, we can conclude this sum is convergent. And now that you have this convergent expression, you can use it to rewrite various observables in the conformal field theory. It leads to the following operator identity. Namely, if you have a general correlation functions of many other insertions, O1 to the ON, as long as they are inserted outside this unit disk of your choice, O1 to ON, you are free to replace these insertions of these two operators, Z1, Z2. You are free to replace this pair of insertions by a lower point correlation function, by insertion of a single operator in this case, with the cost of introducing these z-dependent prefactors. As follows. Okay, and this is the consequence of just applying the following decomposition. Okay, like re-representation of the state in terms of operators, single operator, to this particular correlation function, which you can think of as a matrix element associated with this state, with the state created by the other operators.
Okay. This is convergent in disk of radius z1 minus z2, or
come again?
It's convergent as a, what's the radius of convergence?
The radius of convergence is that I mean the operators, as long as they are outside this this disk, that expression is convergent. Okay.
There's another question?
What is a sufficient condition for state operator correspondence? I mean, is there state operator correspondence in higher dimensional CFT?
Oh, a very good question. So the state order correspondence works in general CFTs. Yeah, there's open question. So in general, QFT is not believed to hold, but there's open question to understand in what kind of QFTs the generalization of state operator correspondence may hold. That's not a QFT. I think we'll hear from Dam Song about the perhaps the generalization of state correspondence for CFTs which are non-relativistic. For the purpose of these lectures, the CFTs are always assumed to be relativistic.
Question is?
Just to be curious,
yeah.
What's the argument that this state over correspondence that doesn't hold in general QFT?
Yeah, so it's coming from the other direction. So perhaps we can discuss that in more detail afterwards. It's coming. So you always have the one direction coming from local operator to state, but to get the map from the state to operators, you have to evolve backwards, and that's a very dangerous thing to do in general. And that to get around that, you have to be able to pick energy eigenstate respect to this radial Hamiltonian. And that's not something that you have in general QFTs. Okay? So this general idea that if you could, in theory, if you evolve in forward in time, that's a very good thing to do because high energy states are damped. But if you evolve backward in time, it's a very dangerous thing to do because high energy states, they get enhanced. But if you can kind of grade your states according to the energy, in this case, the respect to the radial Hamiltonian, you can limit this danger. But that's something you can only do when you have conformal symmetry or dilatation symmetry.
And here you're only considering correlating functions of Virasoro primaries, or?
So for this argument, I'm not using Virasoro symmetry yet. So this also works in general space-time dimension. You just have to interpret the figure differently.
It's just that in 2D, right?
Yeah. No. So this discussion holds in general dimension.
No. But in 2D, non-Virasoro primaries transform weirdly under while or conformal transformations, right?
Yes.
So I'm wondering, in going from the plane to the.
Oh yeah. So I'm putting under the rug potential anomalies. Yes. So you are completely right. There could be additional factors coming from the wild anomalies. Yes. Yeah. Okay. So I'm suppressing. I think I did not discuss that, but at some steps when I relate correlation functions on the plane and the correlation from the cylinder, there could be wild anomalies. Okay. For example, stress tensor 1-point function is 0 on the plane, but it could pick up an additional contribution when you transform it to cylinder.
But that somehow doesn't invalidate.
No. Yeah. Good. All right. Okay. So the upshot here is that as operator statement in correlation functions, as long as you are within the radius convergence, which just boils down to the fact that you can draw a circle that encloses the two operators of interest, you can replace that two operator insertions by a single operator insertion as a cost of including some prefactors. Okay? And these prefactors are highly constrained, as we'll see later, by a small number of numbers, which are known as the structural constants. And all the subsequent z dependents are fixed just as a consequence of conformal symmetry. All right. So now we're ready to talk about constraints from unitarity on the representations of the symmetry here. That is Virasoro symmetry. So as I said before, just as a general property of symmetries, that your local operators, and also if you have a Hilbert space, which is the case in this conformal field theories, they fall into representations of the corresponding symmetry. And in the unitary theory, they fall into not aperture representations, but unitary representations that respect the Hermitian structure and the positivity of the norm on the Hilbert space. In this case, unitary representation of the Virasoro times Virasoro symmetry. And for the rest of the talk, I'll focus on the case where there's no gravitational anomaly. So the central element describing the two Virasoro algebras on the holomorphic and the holomorphic side are the same. There's a question? Okay. And the primary operators, which are distinguished local operators in this context, they are denoted in the rest of these lectures by this corresponding quantum numbers h bar. And they are eigenvalues respect to L0 and L0 bar, respectively, okay, which are Hermitian as a consequence of the Hermitian structure that we described before. And they can be diagonalized, and the corresponding eigenvalues are h and h bar. And they are in one-to-one correspondence with the lowest weight states of each irreducible representations of the Virasoro symmetry, which will sometimes just denote by this by the same labels. Okay. Again, there could be degeneracies which we are sweeping under the rug. And so to understand what are the primary operators and their transformation property on conformal symmetry, that can be deduced by just from the definition of the lowest weight state of these irreducible representations. And they satisfy, as I already said, that the eigenvalues under L0 and L0 bar are H and H bar separately. They have, in addition, this lowest weight condition, namely they are annihilated by operators that lower scaling dimensions as follows for n bigger than 0. And this condition, using the state operator correspondence, dictates how this primary operators should transform corresponding to this lowest weight state. And they transform in the following way. Namely, you have primary operators with holomorphic anti-holomorphic weight H bar. Under a conformal transformation, that sends z to z prime, which is a homomorphic function of original coordinate z, and z bar to z bar prime. Okay? The corresponding operators transform in the following way, with some very simple prefactors that depend on the space-time insertions as follows. Sorry. Z bar prime, z bar minus h prime, and then operator inserted at origin. Okay? And this expression you can derive in many ways. One way to derive them is to look at the infinitesimal level, where z bar and z bar is related by z just by infinitesimal transformation generated by a conformal Killing vector, and then using the fact that these corresponding states are lowest weight state. You can also derive this by realizing that this conformal transformation is a combination of a diffeomorphism transformation, which you know how the operators of corresponding spin transforms. The spin is given by h minus h bar absolute value, together with Weyl transformation. Okay? And the Weyl weight is determined by how the metric changes under the corresponding conformal transformation. And from that, you can deduce the same expression. There's a question.
What is h prime?
Sorry, this is h bar. Sorry. Good.
So if the transformation is not connected to the identity, how do you derive it?
So you mean for the inversion?
Yeah.
Yeah. So that's a good question. There are several ways to do that. You can make it connect to the identity by introducing additional -1.
Okay.
Okay. By introducing it by combining with additional parity, and you can also derive it by consistency of how it transforms under a special conformal transformation. Okay. All right. So with this property, the consequence of conformal symmetries on correlation functions, namely the word entities, has to take this specify the following things. First of all, the correlation functions of the transform operators. So I'll, for the moment, drop the subscripts that labels the corresponding scaling dimensions, and also abbreviate the anti-holomorphic dependence. It says that the transform operators at the untransformed locations, okay, is equal to the correlation functions of the operators before the transformation. Again, I do not mean these operators are purely holomorphic. I just simply drop the anti-holomorphic dependence for simplicity. And there's two consequences. One consequence is that this identity is that the 2-point functions and 3-point functions are completely fixed. Just by this invariance property on the conformal transformation. And it says that the 2-point functions of two operators, 1, 2, with corresponding weights h1, h2, and locations z1, z2, and so on, they are only non-zero if the two operators have the same conformal weights, both on the left and the right-hand side. So let me just focus on the constraint coming from the one copy of Rosoro. So focus on the left conformal weights. And then the corresponding z dependence is given by z1, 2, namely the difference between z1 and z2 raised to the power 2h1. Okay. Again, I'm only giving you the holomorphic dependence. Anti-holomorphic dependence follows in a similar way. And then similarly, if you study the constraints coming from this identity on the 3-point functions of 3 operators, 1, 2, 3, locations z1, z2, z3, conformal weights h1, h2, h3, and so on, you will find that this is equal up to our overall coefficient with the particular position dependence, z1, 2, difference between z1 and z2 to the power h1 plus h2 minus h3, z2, 3. You see the pattern. And z1, 3. Okay? And this number, okay? Once you normalize these operators using the 2-point function, this number are known as the structure constants. And these are the numbers that determine for OI and OJ and O3 taken to be OK. These are the numbers that are fully determine the Cij k as a function of z1 and z2 in the operator product expansion that we wrote before. Okay. And then second consequence of these word entities is that correlation functions So far we're talking about just operators, the operators that are primaries. In this context, Virasoro primaries. The correlation functions of all the other descendants, namely at the level of the corresponding state, that are generated by L minus n, for n positive, or L bar minus n, acting on the lowest weight state. The corresponding correlation functions are completely determined by the correlation functions of the Virasoro primaries. Okay, so it's a dramatic simplification in how the dynamics of the underlying theory is encoded in the conformal field theory. Okay, you only need to know the correlation functions of a relatively small set of operators, namely the Virasoro primary, to fully specify arbitrary correlation functions. All right, so what are the constraints coming from unitarity? And this is also where it's related to what the question that Xiaogang asked before, the simplicity of certain conformal field theories below what's known as the minimum model threshold, the C=1 threshold. So one can study constraints from unitarity at the level of the representation of the Virasoro algebra systematically. It just boils down to the analyzing this simple condition, namely states in the Hilbert space, okay, which correspond to local operators. They should have non-zero states. They should have positive definite norm. Okay. So as a very easy exercise, you can show that the center charge first of all, the center charge, the central element in the Virasoro algebra has to be positive. And this boils down to, this can be derived in many ways, but one way to derive it is just from the positivity of the stress under 2-point function. And in this language, it's coming from the unitarity constraint by analyzing the positivity of the inner product on this corresponding state. Okay, so 0 corresponds to the vacuum state. This is a particular descendant with respect to the Virasoro generator L-2. And using the Virasoro algebra written over there and the positivity of the inner product of this state, you can derive this, this inequality. And similarly, you can also show that h and h bar, namely the conformal weights, left and right conformal weights, and they determine the dimension and spin of the corresponding operator. They are also bounded from below by 0. Okay, these are known as the usual unitarity band. There are two-dimensional versions of the usual unitarity band in higher dimensions. So they can be derived without using Virasoro symmetry. This you can derive using Virasoro symmetry. This just holds in general using the global part of the conformal algebra. And this you can derive by analyzing the inner product on the states coming from the level 1 descendant, for example, L-1 or L-1 bar acting on the primary state, on the lowest weight state. Of course, these are just a small corner of the full set of unitarity constraints you can derive from Virasoro algebra, combined with a hermeticity condition that we derived before. And this full set of constraints can be analyzed systematically, as it's summarized in the Gene Sparks review that I referenced over there. They can be analyzed systematically in terms of what's known as the Gram matrix, which is nothing but the matrix that captures the inner products with various levels of descendants of the primary lowest weight state. So for a given lowest weight state, you construct the descendant of this lowest weight state by hitting Virasoro generators on this state. And you compute their inner product. This set of inner products give you a Gram matrix. And the positivity property of this matrix is required by the unitarity condition. And from analyzing this positivity property, you deduce powerful consequences. So just to highlight a few consequences, you find, first of all, you can determine completely unitary irreducible representations of Virasoro algebra, which I'll denote by MCH. So H labels the weight of the highest weight state. Because the Virasoro algebra factorizes and the hermeticity property also factorizes, for the purpose of representation theory, we can just focus on the one part of Virasoro algebra. And so here, just focus on the holomorphic part. And the corresponding representations are denoted by the center charge together with the corresponding weight of the lowest weight state. And this is the irreducible representation of Virasoro C. Okay. And furthermore, you find that for small center charges, namely for C smaller than 1, there's a discrete set of solutions that leads to the so-called minimum models. Namely, the center charges can take very specific values and takes the form of 1 minus C6 over m times n plus 1, where the value m can take to be 3, 4, 5, and so on, okay, increasing integers. And the special case here corresponds to the Ising CFT, which you have already encountered in the previous lecture. And this correspond to a generalization of the Ising CFT, namely the tricritical Ising CFT, and so on. And in addition to the center charge being very restricted, the conformal scaling dimensions, namely what determines the spectrum of the CFT, the spectrum of the energy operator, for example, in the radial quantization, are also very constrained. The discrete spectrum, in this case, again, it has a finite number of possibilities when you focus on the highest weight state. They are given by this formula, famous formula, that you can, again, find in many references as follows. Importing the minus 1, where this R and S are natural number. They are positive integer indices. They are bounded by M, which labels these minimum models from above in the following way. And there's a further identification between this set of possible pairs, R and S. Again, the detail you can find in the references provided. Okay. So in the last, I guess we have last 5 or so minutes, let me describe the particular solution, namely the Ising model. And we'll play many games with the Ising model, or Ising CFT, in the subsequent lectures. So it pays to say something more explicit about it. And you will practice with various features of the Ising CFT, including this partition function and corresponding function and so on in the exercise. Let me just at least introduce the notation. So that's equal to 1/2. That's the icing CFT. In this case, they correspond to m equal to 3 in that whole sequence of minimum models. And the corresponding h's you can figure out by drawing this table of corresponding values of R and S. So R goes this way, S goes this way. S takes 3 possible values, R takes 2 values because m is equal to 3. And these are the possible values, if you can read out from the dimension formula. And taking into account this additional identification, which I did not describe, you conclude the possible values of H, which are compatible with unitarity, are just this possible. There are just the 3 possibilities, and they describe the critical exponents of the icing CFT, which agrees with the critical exponents which you measure, for example, from the either the transverse icing model at the critical point or on the statistical two-dimensional icing model at the critical point.
You say H equals H bar?
Yes. So for the, I'm just talking about the, so far I'm talking about just representation theory, and I have not talked about the modular invariant yet. It's coming from further constraint on CFT. We'll see that there are constraints between H and H bar. Okay. So far I'm just talking about the possible values of H and H bar. I have not justified why H and H bar has to be the same. And to justify that, which will be the purpose of, but maybe let me get that started, to further, to address Zohar's point, to further constrain the possible values of the possible correlation between H and H bar and whether there are degeneracies. So there's related to the question asked before. Once we know what representations are possible, there's still the possibility that each representation can appear multiple times, right? So to address these 2 things, first of all, the potential correlation between H and H bar, namely the weights on the left and right side, and as well as degeneracies for given H bar, we have to study additional constraints on the CFT coming from the basic principles of locality. And this is one way to fix that is to study the locality constraint coming from studying CFT on torus. So exploring locality constraint in a particular observable, and I should have emphasized before, locality for me means that I can define my quantum field theory on the general spacetime manifold, and I'm free to choose, so I'm working the Euclidean signature, and I'm free to choose my spatial slice to quantize the theory, and the choice of this quantization would not change the observable. Okay? At the level of the torus, as we'll see, this leads to this so-called modular invariance property. And of course, CFT on the torus are also interesting for other purposes. For example, understanding the CFT on the finite temperature, okay, at the equilibrium. All right. So how do we study the CFT on the torus? So you can think about the torus in 2 different ways. One way to think about the torus is to think about it as a quotient of the complex plane so let me call the complex plane with coordinates w. And one can think about the torus as a quotient, T2, of the complex plane by discrete identifications, 2 pi according to the following lattice. Okay, and then the tau here is the so-called shape modulus parameter that correspond to the location of this point in the W plane. And this point is normalized to be at location 1 on the real axis. Okay. In particular, tau has 2 components. So this tau is not to be confused with the Euclidean time on the cylinder that we used before. This tau is now referred to the complex modulus of the torus. Okay. And tau 2 has the property that it's bounded from below. Okay. So that's a choice we make, and they're just related by reflection. So this is non-negative. And this torus bonding function you can write in the following way. Once you know once you understand the Hilbert space of the theory on the spatial circle, so you imagine that because you are doing this discrete identification, you can think about this direction as a compact circle, and the Hilbert space on the circle is specified by the previous discussion, and then this torus bonding function, the bonding function on this geometry, is characterized by a trace over this Hilbert space. And this trace involves, obviously, the translation along the time direction that's generated by the Hamiltonian, which I'll denote by H cylinder, because this is naturally related to the theory on the cylinder by gluing top and bottom. So this is the same W that we used before. So let me use sigma plus IT. So this is the Euclidean time. Okay. So to just distinguish between t and tau. So before we use tau over here. By gluing the top and bottom, you obtain the same torus. And the fact that the torus is slightly slanted in this direction is keeping into account by a shift according to the translation in the spatial direction on the Euclidean torus. And that's given by this additional factor. Okay, so again, this H cylinder denotes the time evolution in the cylinder time direction, and this P cylinder characterizes the translation along the spatial direction. And this is where, related to what Max asked before, this is different from the L0 plus L0 bar, the dilatation operator on the plane, precisely because this conformal transformation on this stress energy tensor, which is not a Virasoro primary, it has additional contribution coming from the Schwarzian. And this is equal to, as a consequence of that, is equal to L0 plus L0 bar with additional shift that's coming from the central term. Okay? This is different from the dilatation operator on the plane by this shift. And this shift is coming from the Schwarzian. And it's a consequence, abstractly, it's a consequence of the fact that the stress energy tensor is not a Virasoro primary. Its transformation is more complicated. It has an inhomogeneous term that leads to this piece. Okay.
Would you say that for primaries there is no subtlety in going to the cylinder? And going to the sphere or other components?
Tell me again.
Primary.
If something is a primary.
Oh yeah, I mean, of course, there's still subtlety there. It's just that here, cylinder, we're in 2 dimension. On the cylinder, there's no conformal anomaly. Oh yeah. Yeah, because it's important. That's a very good point. Zohar makes a very good point. In general, when you do Weyl transformations, which is related to going from the plane to the cylinder over here, when the geometry is non-trivial, for example, there are non-trivial curvatures, we have to worry about Weyl anomalies. That's even the case you have when you study correlation function of primary operators. But we're in 2 dimensions where this issue does not arise. Okay. So again, there's generalization of this formula also in higher dimension. Okay. For example, if you are in 4 dimension, this C it will be replaced by the conformal anomaly in 4 dimension A. But you have to worry an additional piece that's coming from a particular conformal counterterm in that context. Sorry, a particular counterterm in that context, which will contribute to the Weyl anomaly.
So how about the momentum? It's just L.
Oh yeah, I have not written down yet. So this case is given by L0 minus L0 bar. Okay. So the modification of the stress tensor under this Weyl transformation is such that this is not identified. It's not modified from the generator of the spin on the plane. Okay. All right. So this is the object that we introduce, and in the next lecture we'll understand consequences that we can deduce from this object on the CFT spectrum. Okay, and in particular, we'll derive that H and H bar has to be identified in a particular way. And furthermore, the degeneracies of this H and H bar representations in the Ising CFT is also constrained to be just unique numbers. Okay, and later on, we'll play a game with a similar object in the presence of symmetry twist and symmetry actions. And that will allow us to deduce or derive not generalized symmetries as topological defects, as well as study their dynamical consequences. Yeah, that's the end of this lecture.